Welcome to week 3, optimization 1. And in this one, we're going to try to bring pi down to earth. We just did a strategic plan over the last 2 weeks. Spreadsheet engineering was the focus, a very straightforward computation, but there's a lot of details to it. This week, we are going to look just at product mix. And we're going to develop pictures like this to help us solve for an optimal product mix. An optimal product mix, the product mix itself will be the decisions. So here's what we're going to try to do. We still have Simone Tortzier, and I believe we introduced somebody else into the reading, and that might be Marta Fazzi, yes, here she is, her CFO. And they're going to provide additional insights. They've decided that cost structures are very important. Demand is very important as well. And now they want to get a feel for how many pies should they be making in 2 different lines. Next week, we will consider multiple lines and scheduling issues as well. Next week, week 4, optimization 2, we will also delve into another realm of this business, which is self-insurance of workers' comp claims. Here we're going to map out a single period again model. We have the possibility of doing this in multiple periods, but typically this job is done in a single period, in this case, weekly. Multi-period models, we will delve into that next week again. We'll implement it, of course, in a spreadsheet using pretty straightforward engineering principles, separate worksheets for separate tasks. The results sheet on this one is something that we might develop or not. We'll see how we go along with that. We're going to tell a story on optimization graphically first, because that we need to warm up to what the non-graphical, purely algebraic, with matrices and everything else that we're not going to delve into at any time. What that approach is like really under the hood. You're basically solving simultaneous equations that are hard to solve without an extra oomph. That oomph will be a IsoProfit curve, and I want to introduce that idea, that concept. Again, sensitivity analysis, assumptions, good practice, and how, again, we can use Excel to rapidly prototype a solution. Of course, it helps that we've done it before. And this is what we're going to provide. These are the deliverables. And the deliverables are, yes, where are those deliverables? Here they are. A cost profit analysis molded into a decision model. Now, the decision model we're going to use is going to be basically a maximize profit by choosing how many pies we're going to produce in 2 different pie lines. One is savory, one is fruit. We already know about that. We already know how to build those profit sheets. And we already know how to optimize price in that situation. Now we're optimizing 2 different decision variables called product mix. Subject to demand conditions, which are just going to be simple minimum and maximum. Keep it easy. And technology constraints. Now, the technology comes across in a couple of different ways. But the main way in this model, we don't have capital in this model, are the availability of labor hours. And labor, of course, and the availability of hours is really on also machines and facilities. That's implied. How many minutes does it take to go through a supply chain process, set of processes or sub-processes? So that's what we're going to model, and we're going to need data to be able to do that. data will be coming from Marta Fazzi, the CFO. But there's also a design constraint, how much dough versus how much filling per pie. That's a design constraint. So there's technology and design in this. Here are the resources, of course, to help us along the way. And several of them are right here. Now, what I want to go through are a couple of things, but probably the most important thing is this two-product pie making product mix model. Also referring, of course, to the optimization UNO HTML. Let me bring up the optimization UNO first just to orient ourselves. Here it comes. Yeah, it all started here. You know, I'm always going to give a little bit of a history lesson, but the models we're using go back to Al-Khwarizmi, a Persian mathematician in the golden age of Islamic mathematics and science. And he actually solves a very difficult problem, finding roots of a polynomial equation using diagrams. Now, we too will use diagrams. We've already used the influence diagram. Okay, and if you understand this Arabic script, wonderful. I do not. I have to, I know a little bit about it, but I'm not hardly enough to translate this. Frederick Rose, who is cited here in 1881, translated this. It's still probably the go-to translation for this mathematician. Now, I also want you to be aware that there are other models. There's allocation models. That's basically what we're going to be looking at. There are also things called covering, blending. Blending is kind of also what we're doing, and network. Now, this is the typical conventional way of looking at the menagerie of models, and there will be a separate video and a separate set of worksheets that will illustrate some more of these models. We are actually going to use a network model toward the end of next week for optimization 2. But you're gonna see it's all basically the same kind of model, but with different tricks inside of it. That's the only way I can put it. Tricks. Yeah, algebra tricks, right? Yeah, tricks up your sleeve. Now, the three questions that you're always going to ask about a decision model are these, and we're finally getting to this. What are we deciding? How are we going to define success? And it might be life expectancy, it might be profit, it might be compliance, it might be minimum costs, might be maximum revenue. Each one of these will have implications for what we are deciding, subject to how are decisions, but really how is success constrained. The trade-offs that we're going to find out between decisions will end up as a negative slope in a straight line curve. It'll be as simple as that. Ninth year algebra is all we're going to need to use in order to complete our tasks here. We have data from the company. We're still working for the company. Here's some margin data, which gets right down to net profit per margin and marginal profit per unit. So the net profit per unit includes everything, including allocated fixed costs. Now, allocated fixed costs are irrelevant, and this is something you got to think about. They're absolutely irrelevant to the decision of should I or should I not make a new fruit pie and not make a new savory pie. They're absolutely irrelevant to that, because allocated fixed costs, no matter that we can allocate them by unit or however mathematical method we might use to track fixed costs, their manufacturing overhead, their selling and administrative, as the usual ones here. And there's also some sort of depletion related to the wear and tear of machines and so on. These things are going to occur whether you operate or not. Maybe not the depletion, but it depends. Whether you operate or not. Okay, and that's the key to understanding things like sunk costs, things like overhead and fixed costs. So we're going to go to the marginal revenue per unit. Variable cost per unit will be our cost. We have a marginal profit per unit. And look at all the variable costs: direct materials, direct labor, variable manufacturing, variable selling administration. So we've already pulled out the things that matter to making another fruit pie or making another savory pie and the trade-off among them, okay? And then there's filling and dough also here. These are per unit, and look at the design, 50-50 filling and dough for savory, and it's roughly 60-40 filling and dough for, that's the design of a fruit pie. That's all that will matter. And we go on to another worksheet. We're going to see availability and capacity. Now, the availability is some sort of analysis. Notice the 14-column analysis pad in a spreadsheet. Thank you, Dan Bricklin and buddies, across different processing sub-processes. So this is part of the supply chain. So we're actually modeling a supply chain vis-a-vis the most important input in our mind at the moment is labor, and what is labor capacity per week. And you can see the computations here. How many, it's on FTE, not head count. That's an important distinction. Think about FTE as opposed to head count. You can have lots of people in one full-time equivalent. Days, how many days? We're working all around the clock here. Hours per day, hours per shift, shifts per day. All of these are knobs you can twist around in the design of availability and capacity. We have unit costs, and here's the 60-40 and the 40-60. See how we just get it out of this very, very simple in terms of unit costs being the design for dough and filling. Kind of interesting how we might go about that. And then direct materials is an inventory problem that we're going to come back to next week. We have beginning inventory, additions to inventory, deletions or usage from inventory. We get a usage total out of that, and an ending inventory. So it's beginning plus additions minus usage equals ending. And then we get an average availability as ending inventory plus usage. And that's how we're working the availability. We can come up with other definitions. We can include safety stocks, economic order quantities, all of the usual things that we would learn in operations in this discussion. And I have to say, the hardest thing that I have found over the years is how to compute the two hard things. Going from gross price to net price with all the discounts and everything else on in between. Very hard for companies to get a true handle on that. And the other one is the cost of goods sold. COGS. What is it? Where does it come from? How does the cash conversion cycle, which is, everybody knows, is how money going out, cash going out, but not yet, is called accounts payable. And cash coming in, but not yet, is accounts payable, plus inventory. Accounts receivable, I'm sorry, minus accounts payable. Receivables are cash coming in eventually, plus inventory. And now how do we value inventory? And then how do we take that valuation of inventory and period by period by period, replenish it, deplete it, replenish it, deplete it. It's like a log going into a burning fire. How do we do that? FIFO, LIFO, average cost, market, today's market value of inventory. There's all sorts of different ways. We are not going to get into that. There's a whole other course dealing with that. But be aware of it. And here's the processing. How many minutes it takes to do a single pie at staging. Whatever staging is, we can invent ideas about what it is. It's basically setting up all the ingredients, making sure all the work surfaces are taken care of, washed, ready to go, on the go. All sorts of supplies are available, all the ingredients, all of the pans, all of the ovens, staging. It's all set up. A minute per pie. And then we have assembling all the materials, putting it together. You can imagine making a pie, right? You got to roll out the dough to a level of consistency. You might use a machine to do this, which is typical. A kneading machine, a big Hobart. Having worked in big kitchens, the big Hobart machine, kneading everything, putting it all together. We have the walk-in refrigerator right there for all of the materials, the dough and the filling, and then the actual baking, putting it all together. And how many minutes does it take to bake? Okay, how many labor minutes? People watching it, monitoring it, modifying it. That's what's going on in the baking. Packaging, pretty straightforward. Pop it in, whatever, and it's done. And then you store it somewhere. We don't have storage in here, by the way. Storage costs, holding costs, insurance around that per unit matters. As a matter of fact, our insurance cover is probably in the both the manufacturing overhead fixed costs and in the selling and administrative costs. That's usually where it hangs out, okay? And we figure out a gross capacity out of that. Look at the simple formulas for these things. We sum things up, gross capacity, some sort of factor saying that we take a haircut on this, like me, and say this is our maximum capacity, and that's a management plug there, which may come from experience. There may be data that we could challenge that with. Okay, so we have a lot of data here. How do we transform that into a model? Well, it's almost there already. So let's go back to the three questions. Decisions. What are we deciding? We're deciding on two things, fruit and savory, but there's a trade-off potentially between them. So here's the min and max of those decisions. Given market experience, our marketing folks come in and give us a pretty good eyeball on this, and we can change these goalposts. All right, this gridiron, if you will. But right now, our feasible space is just this four corners. Those are the only feasible levels of fruit and savory that matter. Everything else doesn't matter. It's that simple. And of course, everything is positive. All fruit is positive. All savory is positive. Can we buy fruit pies and then resell them and savory? Absolutely. Trade is not in this model, but we can put in two trade variables. So we're going to positively sell, and we can negatively buy back. We could do that in the algebra. Here is the algebra. It's an inequality. It's a compound inequality. Watch this. Okay, you're probably having lucid flashbacks to algebra classes that maybe you didn't care about, and somebody may have even told you you never use this again. Well, you are using it again, and it's a good shorthand for a lot of things. And now, I'm no Bob Dylan, more of a Bruce Springsteen fan, but resources there are constraining, and this is an issue. We have success. It is called profit. We have a profit trade-off. I go into a whole spiel here, please read it, on how to formulate all of our equations. X is fruit, Y is savory, number of pies. They're all going to be linear equations like this. First order polynomials, X to the first power, Y to the first power. And we're going to have some sort of simple expression. What we do is we can, and here's an example of marginal costs and marginal profits and so on. But I transformed this. Don't gag yet. It's not that bad. Okay, but I go through all of the steps. I don't tell you what the steps are. I am an algebra teacher in that sense, but not all the way. But you can see all of the steps. Anything added to both sides, anything you add must be done to the both sides. Anything you divide must be done to the both sides. Anything negative to one side, multiplication, must be done on the other side, with the exception, and it's going to be an important exception. If you have an inequality, it switches the direction of the inequality. Please never forget that. It'll cost you in statistical decision models if you forget that. And we use simple algebraic facts. Okay, lovely there. Yeah, things become one, things become zero. Now this is AlQuery's. This is what he showed us how to do. How to solve an equation like this. More importantly, he was interested in solving quadratic equations because he knew, and we know, quadratic equations kind of make the world go around in a lot of ways, at least at the macro level, not at the quantum level. And by the macro level, I mean our net profit curve was quadratic in prices and prices squared. The same with our weekly profit model. Here we have IsoProfits now. And so I take these equations and transform them into an intercept at the top and a rise over the run, which is the slope. And there's another intercept. There is an x-intercept. You could just take these, 20 to 20. Not quite. You can see it's almost a 1-to-1. So the ratio of these coefficients is the trade-off. My gosh, here it is. The ratio AB, AX, BY. That is the trade-off. That's how we speak about it, trade-off. Like an odds ratio, too, if this was stats. And then I wander and show that the change in number of savory pies per change in an extra, and that is D. This is calculus. If you don't know calculus, fine, learn some calculus. It's a great set of concepts. Great set of concepts. I take a total derivative and I manipulate it, assuming that C in this case is the profit to 20,000 or 40,000. I vary it. If it doesn't change, what is the trade-off? Doesn't change means it's on the same line. If it does change, look at what happens. Small profit at the bottom, parallel shift to the right, more profit, 40,000. Another parallel shift to the right. Well, look what's inside here. The profit line with these two constraints. Okay, only this box is important. Then we get there. I can actually solve this just like this by moving one of the profit lines over to the maximum profit combination of savory and fruit. It is as simple as that. And that is what the algorithms do. It's what George Danzig did in 1949 with a guy by the name of Marshall working for the US Air Force on logistics, basically. They're just working logistical models, minimum cost models, maximum effect models, benefit models, using exactly this. This is what we call in the business a technology. Yeah, absolutely. Using this technology, constraints and trade-offs, but we keep it simple. Well, computing in those days had to keep it simple. They had to keep it very simple. And they're basically solving a set of what we call underspecified simultaneous equations. They won't solve. They'll solve for a range, but not for a point within that range. The problem is, how do you get them to solve within? There's a lot of possibilities. That's feasible. That's what's feasible. That whole gray area is feasible. What's the best one? Well, you can eyeball what the best one is, because when that profit line moves to the right, there's more profit. The satisficing criteria increases, and we want to get the most subject to this constraint. Not without constraint. There we go. Now we have throw up the sticks time. the name of this week, really. Throw the sticks up and see where they land. Well, they're not parallel to one another. We have two lines here. Can you spot them that are parallel? Well, if they're parallel, the ratio of A and B is exactly the same. We have an X plus Y packaging and an X plus Y staging, different levels, less than or equal to a 13.4 or 21, 20.1, thousand minutes. You can tell which one is which. The 13 is the purple one and the blue one is staging. These are relatively redundant to one another. And the one that matters between the two is going to be packaging, because it cuts the space more. So it constrains. It's the minimum. We're going to look for a minimum set of constraints. That's what we're going to try to cut the space down to the common denominator. It's included in the blue, and the purple is included in the blue. Okay, but the blue is not included in the purple. And then we got other ones. We got two crisscrosses, a red, and these do have different trade-offs and a point. Look at that point. That point's going to be kind of important to us. That's assembly and baking. We also have filling and dough to throw into the mix. Here's filling and dough, and they too have differential trade-offs. Okay, and they have a point at which you see, when you have lines like this and a point like that, you have two equations and two unknowns. That is perfectly specified, not under, not over. We can solve. But now we have four equations in two unknowns, basically. And well, that's a little bit too much underspecified. So we take out some redundancy. You can read through this and look at it. We take out that and put in material. So now we have two lovely little trade-offs. We have 2 points here, but still the green and the red are all included in the other constraints. The other constraints are not completely included in this green point down to the red. This area at this bottom part is going to be our final constraint that we're going to deal with. And then we throw onto it a maximizing constraint here for savory and fruit. This one's not going to matter so much. The fruit might matter. Yeah, but look, I think you can see that this has to be the solution. It's within the square of maximum and minimum demand. It is got the most feasible set of possibilities, which are all these. But now the feasibility goes from, see where my cursor is, down, over, up a little bit, and then up and over. That little wedge, not quite a triangle, is our feasible space. And we know that when we throw a profit curve on this, we don't want to be down here with the profit curve. We can't be up here with the profit curve. We want to be right here with the profit curve, and let us eat some pie. So assembling, baking, and profit all come together, and it's a beautiful thing. This is the optimal profit, 55,376. Solving for this is over 7,754 fruit pies, 3,102 savory pies. That's the answer. That's the weekly answer, by the way. Throw it in, and pretty much all of the weekly profit numbers, all of that should work to the same kind of model, depending upon the price now. Now, price, remember, we have an average selling price. That's the thing we saw for last time. That's buried inside the 298 and the 295, remember. We have a unit selling price for each of the pies being mixed here. Before, we had it across, so kind of an average. Is there an easier way to do this? Oh gosh, yes, there is. We have an algorithm. We have an add-in in Excel, and that add-in, called the Make a Pie product mix, and this is weekly, should say weekly. Here are all of the different pieces. Notice the preponderance of the use of sum product. It behooves us to go to Wayne Winston, look at sum product. And then it also behooves us to go to Shandoo, shandoo.org, CHANDOO.org. Go to Shandoo and see all the other things you can do with sum product, including filtering. It's a cheap way to produce a pivot table. Matter of fact, I have found it for very large pivot tables to be a much faster and more reliable. It doesn't break. There's a way to break a pivot table very easily, because most industrial applications of pivot tables have dynamically changing ranges, including rows and columns. And when that happens, the pivot table breaks, especially the binding. It's called the binding, the row binding cracks. Okay, that's a problem. Look at how we set this up. We have pies produced. I happen to get the actual solution here. We have the minimum and maximum demand constraints. We have unit selling prices coming from the margin sheets. And we calculated a unit margin here. Okay, good. I like the word margin. And we have a total here, which is the sum product of fruit savory and the 298, 295 unit margin. It's 7754 times 2.98. That's the product, plus some, another product, 3102, 295, voila. Kind of French, I guess, for total margin. Okay. Now, if we go up and look at something else, we might come up with a different number, but that's a different issue. Okay. I might even have a typo up there. Oh, imagine that. But this one seems to do it correctly. And I know we got the right. Yeah, we got the right numbers there. That is exactly right. Well, somehow this is wrong. Well, I'm going to have to look at that and possibly change that, and that will be changed. That's good. Always check your model. This is a check on the model. Used. We do another sum product of minutes 1 times 7754 plus 1 times 3102 equals this. Is it less than or equal to the available? And that's how we compute these. Now notice they're all color-coded, easy to find. Check it out. Works beautifully. Here's how it gets set up. We go to the solver add-in in Excel, go through the process of getting the add-in included. I give you the places to go to in the text here, where to go to get this this model in your machine. It comes packaged with Excel, all operating systems that I'm aware of. And then you go ahead and enter constraints. For example, to enter a constraint down here, we have 3 things you must enter. And notice you can use a range. So you only need to have 1 entry for all of these processing, less than or equal to all of these availability numbers, which come directly from the availability sheet. You say, okay, it pops in. You have another range for materials and available. So the key to this is understanding how to calculate what a particular decision gets to, and then the model tests, solver tests, whether it is less than or equal to, because that's the constraint here, less than or equal to the available. Oh, when you're all done with that, you say solve, press the sensitivity. We're going to get into that next week. Say okay, and you have your model. And you're done. Okay, I hope that was fun for you. It was outrageously fun for me. Oh, I got to put in here. Now, George Danzig, I put here, you have to read this, but I think you should put your fingers in it, econometrica. Danzig's model. It's used by Paul Samuelson and others. Dorfman and Samuelson is what I learned on in the late 60s, early 70s for making models. There's another one called the Leontief. This is input-output analysis, which is the income value-added accounting that we do for whole countries. And I've also done that, for example, for the state of Utah, using exactly the same kind of model. Okay. Very, very similar set. Here's the algebra of Muhammad Ibn Ben Musa in here, but his real name is Musa al-Qadri, Muhammad Ibn. Okay, now it's 1881, but he actually did this around 18, not 18, take 1,000 years off, 30, and we have Wayne Winston. Okay, so, and this is George Danzig's abstract. So you can see it's everything we're doing. A lot of things on top of that. So let me pull this back up to the solution here. Bill has something to do. He has to fix this 55,376 somehow. And I hope that was helpful in going through what we're doing this week. Take care and thanks.